Welcome back everyone. Today's video is an explanation of problem F from the AtCoder Beginner Contest 310. I have provided the correct Python code in the video description, so please check it out after listening to my explanation. Let's begin with the problem statement. We have n dice and the ith dice shows a random integer between 1 and ai with equal probability. So each element in array A represents the maximum value of each dice. Our question is to find the probability to satisfy the following condition when the n dice are thrown simultaneously. The condition is that there is a way to choose the values of some dice so that the sum equals 10. But we need to calculate it modulo the large prime p. Let's check our understanding of the problem with example. See the good cases of 4 throws. 3, 6, 2, 4 satisfies the condition because 6 plus 4 is 10. So we can choose the second and the fourth dice to make 10. 1, 7, 2, 4 also satisfies the condition. On the other hand, 1, 2, 1, 5 doesn't satisfy the condition because we can't get 10 no matter how we chose some dice among them. The total number of cases of 4 dice throws is 504, so the answer for the example is as follows. Let's proceed to solve the problem. First, our target value is the probability, but we will focus on counting the number of the required cases because the total number of cases of n throws is just the product of AI. Then, we should try dynamic programming. Why should we come up with DP? Because this is a counting problem. It involves a similar operation like throwing a dice multiple times, and the order of throwing n dice is not so important. So from now on, I'll show you how to solve the problem with DP. The difficult part when using DP is to prepare appropriate variables and values for it. But first, we will begin with the simplest settings. We will prepare two variables, I and j, and define dpij. When j equals 1, dpi1 represents the number of cases of throwing I dice from 1 to I, where there exists a choice of 10, which means the target condition that there is a way to choose some dice so that the sum is 10. When j equals 0, dpi0 represents the opposite, which is the number of cases of throwing I dice from 1 to I, where there doesn't exist a choice of 10. This definition is natural, because we like to know if the target condition is satisfied or not. Let's see the example below. The tuple 372 is in dp31 because it has a choice of 10. Let variable a be a value of dice 4, and no matter what value a is, the tuple 372 a also has a choice of 10. Therefore, we add a4 elements to dp41 for each element in dp31. Let's also check elements in dp30. 351 and 239 are both the elements in it. Consider the value of dice 4 is 6. Then something wrong happens. 3516 is in dp41 because 3 plus 1 plus 6 equals 10. But 2396 is in dp40. This implies that we can't define the transition equation from DP30, and our definition of DP is not a good one. In general, all the elements in a DP set must move on to the unique set. Our first DP has failed, so let's try to improve it. We've found 351 and 239 in DP30 should be distinct when adding 6, so we need to think about how we do that. You'll find that the difference between them is whether there is a choice of 4 or not. Therefore, we conclude that we need to add a variable to the DP function so that we can remember the information about the existence of a choice of 4. Plus, if you understand this reasoning very well, you'll notice that you also need to know about it from 0 to 10. And you also find that you don't need to care about integers greater than 10. Let's improve DP. Our previous variable j has the information about the existence of a choice of 10. Since we want to know the information from 0 to 10, we will simply use 11 variables like j. But here, we will use just one variable s, which is a binary 11-digit number, instead of 11 variables. When the nth digit of s is 1, it means that the case of throwing I dice has a choice of n. Using just a variable s helps you when you consider transitions afterward. Let's see the example below and check how it works. 351 has a choice of 9, 8, 6, 5, 4, 3, 1, and 0, respectively. We transfer all the information into a binary number. Then we have 0110, 1111, 011. So 351 is in DP3 and this number. Please check the case of 3516 by yourself if you want. In this slide, I'll show you that the new DP solves the problem caused by the previous DP. The problem is that 351 and 239 can't be distinct in the previous DP. But now our DP has distinct sets for 351 and 239 respectively, because the states S for them are completely different. Therefore, we conclude this DP must be well defined. We've defined the DP function, and now we consider the transition between them. For fixed I, S, and A, which is the value of dice I plus 1, what is the next state t? In conclusion, we can write t as in the formula on the right side. I'll explain it with the example below. First, 351 has a choice of 9, 8, 6, 5, 4, 3, 1, 0. When we add 6, newly constructible numbers are 15, 14, 12, 11, 10, 9, 7, and 6. That is just adding 6 to each element in the set. Then we take the union of two sets because every choice from 351 is allowed, even in the case of 3516. Finally, we restrict the set from 0 to 10. The restricted set is the next state t, and this is what we want. This process is easy to express in the binary system. First, to add variable a to each element in S, we just shift S to the left 8 times. Then we take a bitwise OR of S and left shifts of S by A to obtain the union of the two sets. Finally, to restrict the set, we cut digits greater than 10, but we can do it by taking a bitwise AND with a binary number consisting of 11 digits, all of which are 1. We call the number x, and x can be calculated as left shifts of 1 by 11 minus 1. Therefore, the state t can be calculated as follows. This is a big advantage of using a binary representation for the state S. Let's summarize the algorithm. We define x as follows. Then we iterate variables I, s, and a from 1 to but not including n, from 0 to but not including left shifts of 1 by 11, and from 1 to ai plus 1 respectively. Then for each I, s, and a, define t as follows, and add dpis to dpit. This algorithm is almost good, but we need further improvement. Since ai is at most 10 to the 6 from the constraints, the iteration of variable a takes 10 to the 6. But you'll find that if a is greater than 10, adding variable a doesn't affect the state s because we are only concerned about numbers from 0 to 10. So in this case, the next state t equals s, and we can just do one step as in red ink instead of iterating a from 11 to ai plus 1. This reduces the number of transitions for fixed I and s from at most 10 to the 6 to at most 11. At the end of this video, let's calculate the total time complexity. The execution time of dp can be calculated as the size of dp times the number of transitions. So it is n times 2 to the 11th times 11. N is at most 100, and 2 to the 11th is about 2000. So the total time complexity is about 10 to the 6, which is acceptable. We have successfully solved this problem, and I have completed the explanation. If you have any questions regarding the problem or any requests to solve other ABC problems, please feel free to comment. Thank you for watching the video.